Derivation of the Maxwell-Boltzmann speed distribution. In this video, we derive the Maxwell-Boltzmann speed distribution of ideal gases using the barometric formula. So let's get started. In the video on the Maxwell-Boltzmann distribution, the distribution function of the molecular speeds has already been explained in detail. The diagram shows the speed distribution for different temperatures. In this video, this distribution function is to be derived. This derivation is based on the barometric formula, which we will discuss in more detail first. Barometric formula. It is true that the molecules in gases are almost not bound to each other by intermolecular forces and can therefore move relatively freely in space. But nevertheless, gravity also acts on the molecules. This has the consequence that the molecules contained in gases tend to move more towards the surface of the Earth. This explains why the particle density of air is greater near the ground than at high altitudes. The density in turn directly determines the air pressure. Therefore, the air pressure decreases with increasing altitude. In this context, the barometric formula describes the decrease in atmospheric pressure as a function of altitude above a reference level. Usually, sea level serves as the reference level. In another video, we derive this formula in detail. In this formula, P0 and ρ0 denote the pressure and density, respectively, at the reference level. In this way, for any height z above the reference level, the respective pressure P can be determined. At this point, it should be explicitly mentioned that the barometric formula in this form is only valid for a so-called isothermal atmosphere. This means that the derivation of this formula was based on the assumption that the temperature does not change with increasing altitude. This does not correspond to reality, but later on, the barometric formula is transferred to gases within which the temperature is constant. Therefore, this assumption of the isothermal atmosphere corresponds exactly to what we will have later actually. In the following, we would like to rearrange the barometric formula in such a way that we can use it to describe the decrease in air density rather than the pressure as a function of altitude. First of all, it should be noted that the barometric formula is not limited to air. It can be applied to any ideal gas which is exposed to a gravitational field. The ideal gas law shows the given relationship between the volume V, the number of particles N, the thermodynamic temperature T, and the resulting pressure P. In this formula, Kb denotes the Boltzmann constant. We will also derive this formula in detail in another video. The number of particles N, marked in blue, contained in this formula, can be determined from the quotient of total gas mass, m gas, and the mass m of a single gas molecule. In this way, we obtain the shown formula. In this formula, we can interpret the quotient of gas mass and gas volume, marked in red, as the gas density ρ. In this way, we obtain the ideal gas law as a function of density. Thus, between the pressure P and the density ρ at a height z, the given relationship applies. At the reference level, denoted by the index 0, this relationship can be established quite analogously. At this point, it should be mentioned again that we assume an isothermal atmosphere for the barometric formula. For this reason, we do not need to differentiate between the temperature at an altitude z and the temperature at the reference level in the two given formulas, since this is the same in both cases under an isothermal assumption. Therefore, the temperature in both cases is denoted by T. We can now use these two relationships in the barometric formula. The red and blue marked terms will then be cancelled out. In this way, we finally obtain the relationship we are looking for, with which we can determine the density at any height z. Since the mass m in this formula refers to a single molecule, the term marked in red can be interpreted as the potential energy of a molecule at the height z. We thus obtain the density as a function of the potential energy of the molecules. At this point, the question arises how the molecules get to their potential energy. First, imagine the gas molecules at absolute zero. Since there is no Brownian motion, all molecules are on the ground at reference level due to the influence of gravity. Now one slowly increases the temperature by heating the gas, so that the motion of the molecules will increase. Sooner or later, the molecules will collide with each other. As a result of the permanent collisions, some molecules will catapult each other higher and higher. From an energetic point of view, this means a supply of kinetic energy at the reference level, which is then converted into potential energy. So we can conclude that the molecules reach their heights due to their kinetic energy at the ground. We can clearly demonstrate this behavior with a simple experimental setup and use it for a model conception. In the following, we will go into this in more detail. Model conception. To illustrate the behavior of gas molecules in a gravitational field, one can conduct the following experiment. One puts many small balls into a vertical tube, which stands on a vibrating plate. The balls will move more or less strongly depending on the strength of the vibration, just as the gas molecules move more or less strongly depending on the temperature. The balls are catapulted into the air, just as the gas molecules in reality do due to their collisions. Through small slits on the side, the balls can exit the tube at different heights. In the process, mainly only those balls that have reached their maximum height will pass through the slits. This means that their kinetic energy has been completely converted into potential energy. Faster balls will largely bounce off the edges of the slits. One will notice that there is no uniform distribution of the balls along the height of the tube, as is also the case with a real gas. This is due to the fact that not all balls are supplied with the same kinetic energy at the bottom of the tube. The balls collide with each other and therefore some are slowed down and others are accelerated. If, for example, an upward flying ball is hit by a faster ball, then the kinetic energy of the pushed ball will increase. This ball will now be able to reach higher heights. If it is pushed by chance by another ball, it will be able to fly even higher. For a few balls, this might happen one or two more times. Such an ideal catapult effect will only be limited to a few balls. Therefore, as the height increases, fewer and fewer balls are found. Transfer of the model conception to gases. The number of balls registered at the different heights corresponds exactly to the course of the density according to the barometric formula. Thus, the idea behind this whole model conception is the following. Imagine the balls at first in a small volume on reference level, so that the influence of gravity can be neglected. For this we push and thaw a plate into the tube. The balls behave in this state like a gas, whose speed distribution we would like to determine. We determine the speed distribution by examining the kinetic energies. We do this by removing the plate and examining how many balls reach which height. By knowing how the potential energies are distributed, we obtain knowledge about the distribution of the kinetic energies of the gas at the reference level in the original volume, since the kinetic energies have been completely converted into potential energies. In fact, we do not have to carry out the examination of the distribution of the energies in an experiment, because the result of such an experiment is already described by the barometric formula. This gives information about the particle density at the different heights and thus about the distribution of the potential energies, which corresponds directly to the distribution of the kinetic energies in a gas. Thus, to the same extent as the density decreases with increasing height, the proportion of those molecules which have higher and higher kinetic energies also decreases. According to the barometric formula, the decrease of the frequency with which certain energies are present follows an exponential course. This term, which describes the exponential decrease of the frequency with increasing energy, is also called Boltzmann factor and plays a central role in statistical physics. However, since we want to determine the speed distribution in a gas and not the distribution of the kinetic energies, we simply replace the term for the kinetic energy with the term 1/2 mv squared. It must be noted, however, that the speed in this formula refers only to the z component of the velocity. Because the starting point of the given relation was that the molecules reach a certain height, and for this only the velocity component in z direction is relevant. For example, a molecule can have a very high speed, but this is irrelevant for reaching a certain height if the velocity is directed sideways. The decrease of the frequency as a function of the speed is shown in the diagram. The frequency curve now has a different course, since the energy is influenced with the square of the speed. Now the question arises with which concrete frequency molecules with a certain speed are present in a gas. Here it must be considered that one will find no molecules which show identical speeds. Even with a large number of molecules, one will find in the end no molecules whose speeds are exactly the same. The speeds will always differ from each other, no matter how small the difference may be. Also, in the model conception of the balls on the oscillating plate, one has in principle the same situation. With 1,000 balls, for example, one gets 1,000 different heights to which the balls reach in each case. No height will be exactly the same as the other. Therefore, one cannot link the frequency to a certain height or a concrete speed. A frequency is therefore always linked to intervals. It is only possible to link ranges of heights or ranges of speeds to a certain frequency. In the case of the oscillating plate, this is done by the finite height of the slots. The maximum height to which the balls reach can therefore vary within the height of the slots. Only this height range can be assigned a certain frequency. So, for example, one can say that at a height between 10 and 11 centimeters the number of balls registered there is 4. With respect to the speed distribution in a gas, this means that we can only assign speed ranges to a certain frequency. For example, we can only specify the number of molecules whose speeds are in the range between 1000 and 1200 meters per second, this means within an interval of 200 meters per second, but not how many molecules have, for example, a speed of exactly 1000 meters per second. Thus, the speeds are divided into ranges with identical intervals and the number of molecules within the respective speed ranges is indicated. The information is usually not given as an absolute frequency in the form of a concrete number of molecules, but as a relative frequency in the form of a percentage. For small intervals, the frequency assigned to the different speed ranges is proportional to the chosen interval width. This can also be seen quite clearly in the model conception with the balls on the vibrating plate. In the range marked in blue with an interval height of 1 centimeter, 4 out of 1,000 balls are present. For the sake of simplicity, we assume in the shown image that all the balls have just reached their maximum height. The 4 balls out of a total of 1,000 balls correspond to a frequency of 0.4%. If the interval is increased to 2 centimeters, then twice as many balls are found in this twice as large range. In this case 8 balls or 0.8% of the total number. If the interval were increased to 3 centimeters, the frequency of finding balls would be 3 times as high. Note that, strictly speaking, this proportionality applies only to very small intervals, since the density of balls changes with increasing height and fewer balls are present in the individual intervals. This proportionality can also be applied to the speed distribution in a gas. This means that for very small speed intervals, the respective frequencies are proportional to the chosen interval width. With a speed interval twice as large, for example, twice as many molecules are assigned to it. Note that this proportionality applies only to very small intervals. But since we will consider infinitesimal intervals later anyway, this limitation will be irrelevant. Let us summarize the previous findings. On the one hand, the frequency with which a certain speed range is present in a gas is proportional to the Boltzmann factor and, on the other hand, the frequency is proportional to the chosen interval width within which we want to determine the frequency. The frequency is therefore proportional to the product of the Boltzmann factor and the speed interval. In order to obtain a formula for the actual calculation of the frequency, a formal proportionality factor f0 can be introduced, so that the following equation applies, which describes the frequency of a speed in the range between Vz and Vz plus delta Vz. For example, one could assume a speed of Vz equals 1000 meters per second and an interval width of delta Vz equal to 200 meters per second. This equation would then tell us with what frequency, given as a percentage, molecules have a speed between 1000 and 1200 meters per second. Note, however, that this speed range refers only to the z component of the velocity. However, we will generalize this to arbitrary velocity vectors later. We can see from the formula that the term marked in red, which contains the Boltzmann factor, corresponds to the height of the bar and the speed interval to the width of the bar. The frequency itself can then be interpreted as the area of the bar. The course of the red marked term is shown in the diagram as a red line and is called frequency density. With this basic understanding of what this equation states, we now want to determine the proportionality factor f0 in the following. Determination of the proportionality factor. In order to determine the proportionality factor f0 in the given equation, we must first consider its meaning. As already mentioned, this equation gives the frequency f with which molecules are present in the gas which have a speed in the range between Vz and Vz plus delta Vz. This corresponds to the rectangular area under the curve of the frequency density. Thus, if we sum up the frequencies over the entire possible speed range, we cover all the molecules contained in the gas. This means 100% of the molecules. Mathematically, this corresponds to the value 1. Note that the molecules can show not only a positive velocity component in z direction, but also a negative one. Thus, the possible speed range of the z component is between -infinity and +infinity, because a molecule must have some speed, no matter if positive or negative. As already explained before, the equation was derived under the condition that the speed interval must be very small. In principle, we can now make the interval smaller and smaller. In the extreme case, the speed interval becomes infinitely small. In this case, we consider infinitesimal intervals dvz and the sum becomes an integral. In this way, we determine the total area under the frequency density function. As total frequency, this area must correspond to 100% or the value 1. Under the constraint that the integral must correspond to the value 1, we can now determine the proportionality factor f0 by solving the integral. For this, we can first write the constant factor f0 before the integral. The red-marked integral is actually not so easy to solve. However, a look into the mathematics formula collection shows the given term as the solution for this integral. In this way, we obtain the proportionality factor. We can now use this factor in our formula. The frequency function is thus completely determined and normalized to the value 1. The diagram shows the course of the red-marked term for a temperature of 300 Kelvin. If we do not want to determine the frequency with which certain speeds are present in a gas over the entire possible range between minus and plus infinity, we solve the integral only within the respective speed limits between Vz1 and Vz2. The red-marked function that we integrate is called frequency density. Thus, the area under this frequency density function corresponds to the percentage of molecules whose speeds lie within the considered range between Vz1 and Vz2. For example, if solving the integral within the limits between 500 and 1000 meters per second gives a value of 0.16, this means that 16% of the molecules have a velocity component in z direction between 500 and 1000 meters per second. Note that the frequency density depends on the temperature. The diagram shows the course of the frequency density for different temperatures. At higher temperatures, the fraction of molecules with higher speeds obviously increases and the fraction of molecules with lower speeds decreases. In a figurative sense, this would correspond to the increase in vibration in our model conception with the balls on the oscillating plate. Frequency density function in 3 dimensions. So far, the speed distribution is limited only to the velocity component of the molecules in z direction. Much more interesting, however, is the distribution of the absolute speeds of the molecules. For this reason, the red-marked frequency density function must be extended to 3 dimensions. In the following, we consider an ideal gas, which behaves equally in all 3 spatial directions. This means that the gas molecules have no direction in which they prefer to move. In particular, the influence of gravity is neglected. Such a gas, that behaves the same in all directions, is also called an isotropic gas. First, let's take a closer look at the velocity as a vector. In general, gas molecules have velocity components in all 3 spatial directions, denoted by Vx, Vy, and Vz. The velocity vector v of a gas molecule can be represented by these 3 components. The absolute value of the velocity vector, just called speed, results from the sum of the squared velocity components, from which we then calculate the square root. Thus, for the square of the speed, the shown relationship applies. We will need this relationship later. For the sake of simplicity, we do not use the vertical bars here and denote the speed only by v. The frequency density function derived in the given form describes the frequency with which a velocity component in z direction is present within an infinitesimal range between Vz and Vz plus dvz. Note that in the following we again consider infinitesimal speed intervals. Therefore, we do not need the integral sign for now. Since we are dealing with an isotropic gas, the frequency distribution in the z direction is basically valid for each velocity component. This means that we also get the same distribution function in y and x direction.
For the speed distribution, the question now arises how often a certain velocity vector v with given components vx, vy, and vz occurs within given speed intervals dvx, dvy, and dvz.
A simple example shows the basic procedure. First of all, it must be kept in mind that the frequency with which certain speed ranges are present in a gas can also be interpreted as the probability with which molecules are found in those speed ranges. For example, if 5 out of a total of 100 molecules have a speed in the range between 500 and 510 meters per second, this results in a frequency of 5%. If one randomly picks a molecule out of a total of 100, then the probability of catching a molecule in the speed range between 500 and 510 meters per second is obviously 5%. So note that the frequency can also be interpreted as the probability with which a randomly selected molecule can be found in a certain speed range. Thus, the frequency function can also be interpreted as a probability function. In the following, it makes more sense for the understanding to interpret the frequency of occurrence of a speed range better as a probability. We now assume that among all molecules in a gas, the x component of a given speed range occurs with a probability of 10% and the y component with a probability of 5% and the z component with a probability of 20%. The overall probability that a molecule has all three given speed ranges at the same time results then from the product of the individual probabilities. In this case, the total probability is 0.1%. Thus, for the overall probability or the frequency of occurrence of a certain velocity vector within the intervals dvx, dvy, and dvz, the probability functions of all three velocity components must be multiplied. We thus obtain the shown formula for calculating the overall probability or the overall frequency. Note that when multiplying exponential functions, the exponents can be summated. Therefore, the sum of the squared velocity components now results in the exponent. According to the relation derived before, the sum just corresponds to the square of the speed. We will interpret the meaning of this equation graphically in more detail in the following. Graphical interpretation. The statement of the derived formula is the following. If one gives a speed v, for example 500 meters per second, and for each velocity component a certain range dv within which the individual components can vary, then the frequency or probability with which all the possible velocity vectors are present in a gas is determined by this formula. The heads of the velocity vectors to which the frequency is related all lie within the volume spanned by dvx, dvy, and dvz. The figure shows possible velocity vectors, which all lie within the specified limits and which can therefore be found with the calculated frequency. For the sake of simplicity, we consider in the following the two-dimensional case with velocity components only in z and x direction. We can later transfer the facts to 3 dimensions. Let's take a closer look at the speed in the shown function. It turns out that the information about the direction of the velocity vector is no longer present. Only the square of the speed appears, and this is a scalar. That means, the indicated speed of v equals 500 meters per second does not refer to a specific vector, but to all possible vectors which have an absolute value of 500 meters per second. This is a good thing, because it is assumed that the direction of the velocity does not play a role in the frequency distribution. After all, an isotropic gas was assumed, in which the probabilities for the occurrence of certain velocities should not depend on the direction. Thus, for the frequency distribution, the direction of the velocity is not decisive, but only the speed. What does this mean now for our possible velocity vectors, which may lie within the range limited by dvx, dvy, and dvz? The figure shows another possible velocity vector which has the same absolute value and which may also vary within the given limits. We can also draw another possible vector range. If we represent all possible velocity vectors, we ultimately get a circle in the two-dimensional case, and a sphere in the three-dimensional case, on which the arrowheads of all possible velocity vectors are located. All these vectors can vary within the specified limits. If we draw many more possible velocity ranges, we finally obtain an annulus within which the arrowheads of the velocity vectors may be located. Thus, the frequency calculated using the given formula refers to the percentage of molecules whose velocity vectors lie within the yellow marked range. The figure shows possible velocity vectors. As already mentioned, the velocity v given in the formula does not refer to a specific vector, but to an absolute value. Since the direction does not play a role, it does not make sense to express the range within which the speed can vary by direction-dependent components in the form of dvx, dvy, and dvz. It would make more sense to specify only an absolute value dv for the speed range within which the speed is allowed to vary. We can now do this in a relatively simple way, since the possible speed range obviously forms an annulus in the three-dimensional case with radius v and thickness dv. In the three-dimensional case, the annulus corresponds to a spherical shell. Indeed, this does not look like a perfect annulus or perfect spherical shell. But this is only because we can draw only finite speed intervals. In the limit case of smaller and smaller intervals, the shape actually changes more and more into an annulus or a spherical shell. And finally, we will consider only infinitesimal intervals. Thus, the three-dimensional speed interval can be replaced by a spherical shell with radius v and thickness dv. This shell is limited by two concentric spheres. Due to the infinitesimal distance between the two spheres, the volume between them can be determined from the product of the area of the sphere and the distance between the spherical shells. The surface area of the sphere is calculated with 4 pi v squared. If we replace the speed interval in the formula with this term, then we finally obtain the frequency as a function of the speed v and a speed interval dv. The term marked in red corresponds to the frequency density and is called Maxwell-Boltzmann distribution function. The diagram shows the course of the frequency density as a function of the speed for a temperature of 273 Kelvin. The area under the curve in the interval dv describes the frequency with which the given speed v is present in the infinitesimal speed range dv. For finite speed ranges, the distribution function must again be integrated within the respective speed limits. So note that the area under the distribution function corresponds to the percentage of molecules whose speeds lie within the considered speed range. The influence of the temperature on the speed distribution is shown in the diagram. We will go into this in more detail in another video. Apparent contradiction. If one compares the Maxwell-Boltzmann distribution with the distribution of the velocity components, an apparent contradiction appears at first glance. How can the frequency density at a speed of 0 also be 0, when the frequency densities of the individual components at a speed of 0 are each maximum? If there is a high probability that the velocity components are 0, shouldn't the probability for a speed of 0 also be quite high? At this point, it is important to interpret the diagrams correctly. The diagrams do not show the frequency or probability but the frequency density or probability density. For an interpretation whether a velocity component occurs rarely or frequently, the speed interval must also be considered. This means the area under the curve. The following two-dimensional example is intended to illustrate this and to resolve the apparent contradiction. For this purpose, we consider a relatively low speed and a relatively high speed. For both cases, a speed interval of the same size is given, within which the speed can vary. This interval is graphically represented by an annulus. In which speed range are more molecules found now? In the one with the low speed, or in the one with the higher speed? Let's take a closer look at the figures. In order for the given speeds to be within the yellow-marked ranges, the x components can vary to a certain degree. Graphically, a velocity vector v plus dv whose arrowhead is on the outer circle would just be within the permissible range. The respective velocity component vx is shown as a red arrow in each case. For the distribution of the frequency density of the x component, the previously shown curve applies in each case. The comparison of both cases shows that for a large speed v, the x component can obviously vary in a much larger range without exceeding the given speed range dv. Thus, significantly more x components are possible. How often these components actually occur is shown by the frequency distribution. However, the area under the curve must be considered and not the frequency density itself. The comparison of the blue-marked areas shows that the higher speed is more frequently present, since the x components in question can vary in a larger range. From a mathematical point of view, this is due to the quadratic influence of the speed in the Maxwell-Boltzmann distribution function, which is caused by the spherical shell.
Now it also becomes clear why an extremely small speed is almost non-existent according to the Maxwell-Boltzmann distribution.
Because this would mean that the velocity components should also vary only in an extremely small range. The probability that such a narrow speed range exists is extremely small.
This is shown by the much narrower area under the frequency density function.
In the limiting case, when the speed becomes zero, the x component should in principle not vary at all. The probability that this is the case is zero. Therefore, there are no molecules in a gas with a speed of zero.
The diagram shows the aforementioned quadratic influence of the speed on the course of the frequency density. For low speeds, this coincides very well with the Maxwell-Boltzmann distribution. At this point, the question arises why the Maxwell-Boltzmann distribution flattens out if, as argued, higher speeds should be more frequent than lower speeds. Of course, this argumentation is only valid to a certain extent.
Because as the frequency distribution of the individual components also shows, the frequency density decreases with increasing speed. This means that two high-velocity components are not strongly present anyway due to the limited frequency.
Mathematically, this is described by the Boltzmann factor.
Both laws thus determine the Maxwell-Boltzmann speed distribution. We hope you enjoyed the video and found it helpful. Thanks for watching.